Hello everyone, welcome to Enviro Pioneers. In this video, we shall discuss about different types of orbit in which the spaceborne platform revolve around the Earth and the importance of each orbit in the field of remote sensing. Orbit is defined as the curved path that any smaller object takes around the larger object due to gravity. So here we can see that we have the four orbits: lower Earth orbit, medium Earth orbit, geostationary orbit, and highly elliptical orbit. Normally, the remote sensing satellites are launched in these three orbits: lower Earth orbit, medium Earth orbit, and the geostationary orbit. But higher elliptical orbit is also utilized for some specific purpose. So, as the name suggests, the altitude above the Earth that define these orbits. So lower Earth orbit, it is near to the Earth, and it mainly ranges in between 160 to 2000 kilometer. Geostationary orbit, it is at the altitude of 36,000 kilometer above the Earth's surface, and medium Earth orbit, it is somewhere in between the low Earth orbit and the geostationary orbit. The height of the orbit, that is the distance between the satellite and the Earth's surface, it determines how fast these satellites move around the Earth. Here we can see in this diagram that as the satellite, when it is closer to the Earth, because of the higher gravitational pull, the satellite moves more faster in comparison to the one which is in the high Earth orbit or the geostationary orbit. So here we can see the speed of the satellite, it is lesser in comparison to the one which is in the low Earth orbit, and the one which is moving in the medium Earth orbit is having the intermediate speed. Now depending upon the speed, the distance covered by the satellite will also vary. In this diagram, the length of each red arrow, this represent the distance traveled by the satellite in each of the orbit in 1 hour. So here we can see the distance covered in the lower Earth orbit is much higher in comparison to the one in the higher Earth orbit. Apart from the height, eccentricity and the inclination, these are also very important factors in shaping a satellite's orbit. So here we can see the eccentricity that refers to the shape of the orbit. The eccentricity of an orbit, it indicates the deviation of the orbit from a perfect circle. So when the value of eccentricity is 0, it means the path is a perfect circle. But if it is closer to 1, it will always be less than 1, but as the value it moves towards the 1, it means the orbit is elliptical. Next is the orbital inclination, that is angle between the equator and the plane of the orbit. So if the orbital inclination is 0, it means the orbit of the satellite is just above the equator, and if it is 90-degree, it means the orbit is crossing right above the pole, and if the inclination is 180-degree, it means orbit is above the equator, but the revolution of the satellite is in direction opposite to the Earth spin. So together, the satellite height, eccentricity, and the inclination, these three determine the satellite's path and how much area it will cover on the Earth. Now, on the basis of rotational direction of the satellites, we can have the prograde motion and the retrograde motion. So, the prograde motion is when the orbital or the rotational motion of the satellites is in the same direction as we are having the rotation of the Earth. So, here we can see the Earth rotation is from west to east, and the satellite is also revolving in the same direction. So this type of motion or the orbit is referred as the prograde orbit. But when the satellite motion is in opposite direction to the rotation of the central object, or in our case Earth, then it is referred as the retrograde motion and the orbit is referred as the retrograde orbit. Let us discuss each of the orbit in detail one by one. So we shall start with the high Earth orbit. When a satellite is launched and it reaches a height of about 36,000 km above the Earth's surface, it is referred to enter a sort of sweet spot where the orbit of the satellite, it matches the Earth rotation. So here we can see in this diagram that the satellite is revolving around the Earth in the same speed in which the Earth is rotating on its axis. Satellite they revolve around the Earth above equator from west to east, and they travel at the same rate as the Earth, means it complete one revolution in 23 hours 56 minutes and 4 seconds. And because of the same speed, the high Earth orbit is referred as the geosynchronous orbit, because the speed of the satellite is synchronized with the rotational speed of the Earth. Then there is another term, geostationary orbit. So there is difference between geosynchronous and the geostationary orbit. So geosynchronous orbit is if the satellite is reaching at the altitude of 36,000 kilometer in any inclination plane, then its revolution speed will be equal to the rotational speed of the Earth. But if the inclination plane is zero, it means the satellite is above the equator, then only it will be considered as the geostationary orbit. Here it is mentioned, a satellite in a circular geosynchronous orbit directly above the equator. Eccentricity is zero, means it is completely circular, and inclination is also zero. It means the orbit is above the equator and it is revolving in the same direction as the Earth. So in that case, the orbit is referred as the geostationary orbit, means it will be stationary with respect to a particular position on the Earth's surface. Geosynchronous and the geostationary orbits are the prograde orbits where the spacecraft is moving in the same direction as the planet. When the satellites are placed above the equator at the altitude of 36,000 km, these orbits are referred as the geostationary orbit because they appear to be stationary with respect to a particular position on the Earth. The speed of the satellite is synchronized with the rotational speed of the Earth, and this particular satellite will always cover a particular area on the Earth. So here we can see that this particular portion is always getting covered by the satellite because it is moving in the same speed as the Earth is getting rotated on its axis. Now these geosynchronous orbits are also referred as the Clark orbit, or the satellite in these orbits are described as being in the Clark belt in honor of famous science fiction writer Arthur C. Clarke, because the idea of the geostationary orbit came from his fiction. A single geostationary satellite has a line of sight covering one-third of the Earth's surface. Means it can observe a third of Earth's surface when it is positioned above the equator. So if we have the three satellites in the same orbit separated by 120 degree of longitude, they will provide the coverage of the entire planet except for the area above the north and the south pole. So here we have two geostationary satellites in the same orbit, and each of the satellite is stationary with respect to a particular position on the Earth. These geostationary satellites can be utilized in the telecommunication for the long distance and the mobile phone communication or the internet connectivity. It can be used for the broadcasting, television and the radio programming and weather forecasting. It provides real-time information about the weather patterns and the storm system, because these satellites they are stationary with respect to a particular position on the Earth. They will be giving us continuous data which can be utilized for the short-term oceanic and the coastal phenomena, and it can be utilized to detect the wildfires. GPS and other navigation system, they use the geostationary satellite as the reference station to provide a known calibration point for the GPS receivers. Next is medium Earth orbit. It refers to a specific region in space which is between the low Earth orbit and the geostationary orbit. So it lies between 2000 kilometer to 35,780 kilometer from the surface of the Earth. And within the medium Earth orbit, we have two categories. One is the semisynchronous orbit and the other is Molniya orbit, which is the higher elliptical orbit. So semi-synchronous orbit, it is near circular orbit. It is not completely circular, but it is having some eccentricity. So the value of eccentricity is less and it is a near circular orbit and it revolves around the earth at the height of 20,200 kilometer above the surface. And the satellite at this height, it takes 12 hours to complete an orbit. And as the satellite moves, the earth also rotates on its axis. So because of this, in 24 hours, the satellite, it crosses over the same spot on the equator twice every day. So semi-synchronous orbit, it is nearly circular and the inclination, it can be 0 to 180 degree, and here the orbit is consistent and highly predictable. And because of the consistency of the medium Earth orbit, these are mainly utilized by the GPS satellites or the satellites which are used in the navigation purpose. The other category is the Molniya orbit, which is also the higher elliptical orbit. It was invented by the Russians for observing the high latitudes. Generally, the geostationary orbit is valuable for providing the constant view, but the satellites which are in the geostationary orbit, they are placed above the equator. So, they don't work well for the northern and the southern locations because these fall on the edges of the view of the geostationary satellites. So, the Molniya orbit, it offers a useful alternative of the geostationary satellites for the higher latitudes. The Molniya orbit, it combines the high inclination with high eccentricity. So here we can see it is 63.4, means it will be covering the higher latitude and the path is highly elliptical. And because of this shape, the speed of the satellite, it varies. So when it is near to the earth, it is accelerated by our planet's gravity, and the satellite, it moves very faster when it is close to the earth, and as it moves away, the speed, it slows down and it spends more time at the top of its orbit when it is away from the earth. So one revolution, it is completed in the 12 hours, but it spends two-thirds of its time in one hemisphere and one-third time is taken here. So because of this variation in speed, it will stay in space for majority of the time and it will give the persistent coverage for a particular area. So this is the alternative of geostationary orbit for the higher latitudes. And the last is low Earth orbit. As the name suggests, these orbits are close to the Earth's surface, and these orbit, it may be in the range of 160 to 2000 kilometer altitude. Most of the commercial aeroplane, they do not fly at the altitude above 14 kilometer. So the lowest low Earth orbit, it is more than about 10 times higher than that. So the height of the low Earth orbit, it will be always less than 2000 kilometer, but it could be as low as 160 kilometer above the Earth. Satellite in low Earth orbit takes about 90 minutes for one complete revolution. Thus, the satellite travel around the Earth on an average about 16 times a day. So these low Earth orbit may have the different inclination plane depending upon for which area and for what purpose the satellite have been launched. Within the low Earth orbit, a spatial orbit, when the inclination is 90 degree, means the satellite will be passing over both the poles. That particular orbit is referred as the polar orbit. So here in this diagram we can see the highly inclined low altitude orientation in which the satellite is passing over both the pole, north and south pole. So this particular orbit is referred as the polar orbit. Satellites in polar orbit, they pass over a complete different area on the planet because of the rotation of the Earth. And using a polar orbit, a single satellite would observe every point on Earth twice in 24 hours. Ideally, the polar orbit should have the inclination of 90 degree, means it should pass exactly over the pole. But if any deviation within 20 to 30 degree from the polar axis is still classed as the polar orbit. Here we can see this particular orbit, this red line, it is not exactly above the pole. It is slightly deviated from the polar axis, but still it is considered as the polar orbit. And these orbits are at low altitude between the 200 to 1000 kilometer. Within the polar orbit, we have the Sun-synchronous orbit, which is a particular kind of the polar orbit where the satellite is synchronized with the sun's position so that it can capture the images or the data with the consistent lighting condition. Here we can see this particular orbit which is nearly polar, and the angle of the orbit is maintained with respect to the sun position on the earth. And this is the specific type of orbit in which satellite's orbital plane, it rotates around the earth at the same rate as the earth orbits around the sun. And because of this synchronization between the satellite orbital plane and the sun position, the satellite, it passes over a specific location on the earth at the same local solar time during each of the orbit. So to achieve a sun synchronous orbit, the satellite's orbital inclination and the altitude are carefully selected. The inclination is nearly perpendicular to the earth equator, and it is around 98 to 99 degree, not exactly polar, but it is considered as the polar orbit. The altitude is adjusted to ensure that the satellite's orbital period, it matches the earth rotational period. Now we can understand this line from this diagram. Here we can see the position of earth throughout the year. The green line, it represents the sun synchronous orbit, and as the earth orbits around the sun, the satellite orbital plane, it rotates in such a manner that it always maintains the same orientation relative to the sun. And because of this, the angle of the sun rays on the earth's surface, it remains constant for each of the pass. And the magenta color line, it represents a non-sun synchronous orbit, and we can see that this orbit is not changing with earth revolution around the sun. So in the sun synchronous orbit, the angle of the sun's rays on the earth's surface, they remain constant for each pass, and it is very important in many applications such as mapping or remote sensing. So here we can see that as the satellite is revolving around the earth, it will cover a particular area on the ground. So this is referred as the swath. But with each of the orbit, the different area is getting covered. So we can see here that as the satellite is completing one orbit, the place on the earth is getting little shifted because of the rotation of the earth. So it can be simplified like this, that the satellite, it started somewhere from this particular position on the equator, but when it's completed one revolution, it is reaching to the next path. Likewise, in second orbit, it is reaching to the next adjacent position, and this arrow, it is showing the rotational direction of the earth. So likewise, in third orbit, it will be covering another path. So the sun synchronous orbit, it gives the coverage of entire planet, and if we simplify, this can be considered as the path of the sun synchronous satellite. So we are getting the coverage of the entire planet. So these sun synchronous satellites, they provide the best view of the planet, particularly of the areas that are often difficult to cover. And these orbits, they are very important in the scientific studies because during the acquisition of the data, they keep the angle of sunlight on the surface of the earth as consistent as possible. But this angle, it changes from season to season, and this consistency during the acquisition of the data, it provides us the facility to compare the images from the same season over several years without much effect of the extreme changes in the shadows or the lightning. There is one term referred as the nodes. Nodes are the points where an orbit crosses a reference plane. So here the reference plane is the equatorial orbit. So this particular point is referred as the node. So on the basis of the direction of the satellite, these nodes are descending or ascending node. When the satellite is moving towards the north and when it crosses the reference plane, it is referred as the ascending node. And when the satellite is moving towards the south, it is referred as the descending node. So satellite in the sun-synchronous orbit, they mainly pass from the north to south on the sunlit side and from south to north on the shadowed side, that is the ascending node. So during the descending pass, the sensors which depend upon the reflected solar radiation, they acquire the data, and during the ascending pass, the radar or the thermal sensors which do not depend upon the solar radiation, they capture the data from that particular area. So for both the pass, we can have the acquisition of the data in one complete revolution. Most of the scientific satellites and the weather satellites, they are in nearly circular low Earth orbit, and the satellite's inclination that depends upon for what purpose these satellites are launched. For example, the tropical rainfall measuring mission satellite, it was launched to monitor the rainfall in the tropics. Therefore, it has the inclination of 35 degrees, maintaining its position near the equator. And the polar orbiting satellites, they are generally used for the photography and the mapping. These are some of the references from where the content have been taken for compiling this video, and the animation have been taken either from these website or from the Google images. If you find our videos easy to understand and whether we are able to simplify the concept or not, please let us know in the comment section. Thank you all.